So let's have a look at actually how people play this game. There's some interesting experiments we can have a peek at. So here are some numbers from a class, a Stanford game theory class that I taught last year. And these are the numbers of how people played at each node. So the students were asked, what would you do if you were player 1 at the first node? What would you do if you were player 1 at the third node, and so forth? And what would you do if you were player 2 at the fourth node, and so forth? So they were asked at each situation, what would they do? And in these cases, the numbers of how many people said stop at each node are listed here. So 90% of the class, when given the chance at the last node, stopped. 80% stopped when they were player 1 at the second to last node, and so forth. So we get these down here. Now, are these consistent with Nash equilibrium? Well, no. Here's 53%. Nash equilibrium should have this be 100%. So the players are not all stopping. Some of them are passing it along. And in particular, it's probably because they anticipate that they can get higher payoffs if they pass and the other player passes, at least for some set of nodes. So this is a situation where we see a prediction of Nash equilibrium, which is very stark, and we see a different play by the individuals in the actual game. We see some play which is consistent with what players should do if they're put in that situation, at least towards the end. But when we look at the beginning of the game, we're seeing play that's just very different from the Nash equilibrium play. This is what we got out of a Stanford class. Here's a set of results from an experiment by Richard McKelvey and Tom Palfrey. It was published in Econometrica in 1992. And what do we see here? Actually, we see even starker results. So in their experiments, only 1% of the people stopped at the first node. And they get similar results in the sense that the vast majority of people stop when given a chance late in the game, but they're seeing much more passing along and less stopping at early nodes in the game. So if you look at a comparison between these things, the Stanford students and the McKelvey and Palfrey experiments actually played quite differently. Okay, so let's talk a little bit about why we're not seeing a Nash equilibrium in this game and what to conclude from that. So there's a number of reasons why we might not be seeing Nash equilibrium here. One is that it might be just a bounded ability to reason. So when we actually go through the reasoning of exactly how this game should be played, there is a lot of iterations of logic that are needed to unravel things and to make this conclusion that that equilibrium play has to involve stopping at the first node. And there's two ways in which that manifests itself. One is that a player might not be able to figure that out for themselves. The other is maybe they can figure it out, but they're not sure that the other players can. And if they're not sure that the other players are going to stop, then that's enough to get them to want to pass. Or they might not even be sure, maybe they can figure it out, and maybe they think the other players figured it out, but they're not sure the other player is sure that they've figured it out. Right? So we can go on with this kind of logic of iterative reasoning. And we realize that equilibrium puts strong restrictions on this, and it's quite possible that the players haven't got full confidence in the rationality of themselves or the other players, and that can lead to play which differs from the equilibrium predictions. It might also be that there's some altruism, right? So if we look at the last point, when we get to the very end of the game, then the fact that players are not all stopping would indicate that they actually possibly value the other player's payoff, or that they think it's better to give, to have a higher total than to have something themselves. If that's the case, then in some sense we can think that maybe we've misspecified the way that we're writing down payoffs. So there's sort of primitive payoffs, and maybe if players are maximizing something else, then that's something that should be picked up in the game that we're not picking up. So it could be that players are altruistic, or maybe they just believe that other players might be altruistic. So even having enough of a belief that some other player might continue to pass is enough to get them to pass in this game. So we can begin to see that in in games that are a little more complicated than very simple ones, we can begin to get variations of behaviors that might move us away from equilibrium play, at least in the short run. Now, this doesn't mean that game theory isn't a useful tool. It just means that we'll eventually have to move beyond simple equilibrium predictions in order to capture all the behaviors that we might observe in the world. And so that's been a very active area of research in game theory, and we'll talk a little bit about that later in the course. But understanding dynamics, understanding learning, understanding how beliefs are formed, all these things are going to be important in making richer and better predictions about how people play games. Okay, actually, let's take a look at one other set of experimental results on Centipede games, because these are actually quite interesting ones. So these are by Palacios, Huerta, and Volage in the 2009 American Economic Review, so a few years ago. And what are they looking at? They looked at Centipede games, but what they did is they picked very particular sets of players. So instead of just looking at your general student population, they also looked at chess players. And in particular, they got some very experienced chess players. So they looked at how do chess players play against chess players playing the Centipede game. And when they had chess players playing against chess players, they found that actually almost 70% of the players ended at the first node. So quite different than the experiments we just saw, the 1% or the 53%. When they had grandmasters, so these are players who, chess players who are very experienced and have won at many levels and are sort of the highest in terms of their ability to reason and their experience in playing games. When grandmasters play against chess players, this is sort of an amazing result. Basically all of them unravel the game and stop at the first node. So their experience and their ability to play these games lead them to very different behaviors than people who are less familiar with playing games and less familiar with this kind of iterative reasoning. When we look at students versus students, 3% end at the first node, so that's more consistent with the results we've seen before. And actually, interestingly, when you put students against chess players, you get 30% ending at the first node. So the difference between the 3% and the 30% would indicate that at least some of the students are passing at the first node because they believe that there's a chance that other people are going to pass at subsequent nodes. So the fact that they're playing differently against one type of opponent versus another one means that somehow they're taking into account the type of opponent that they're playing in making predictions about what's going to happen, and they're adjusting their behavior accordingly. So that does indicate that beliefs about other people's behavior is very important in understanding the prediction of the games. Okay, let's take a quick look at a couple of other Centipede games just to get some impressions of what happens when you vary payoffs. Here's another version where things are similar except the pie isn't growing. So here we have 10 at every date. In total, it's just the person who stops gets the 10. And if they keep moving, they get 9, 9. So slightly less than 10. So this is a riskier game for player 1 to pass along because player 2 can always, in order to get the 9, 9, player 2 has to pass, but they can grab the 10 at the last point. If we look at what happens in this game, so again, this is from the Stanford class. Basically, in this version of the game, all but one student stopped at every point. So there was one person who said that they would pass along, but all the other students were stopping. We can look at variations where instead we make this up to 11. So now it actually pays for both players to pass along. But again, now beliefs are very important. For player 1 to be willing to pass along, they have to believe that player 2 is going to keep passing. And so we get more people passing, fewer people stopping, but it's not 100%. So some people are playing it safe and grabbing the 10 when they can. And it depends on exactly how confident you are that the other players going to keep passing and what their reasoning is and so forth. You can change it to 10-10 and so forth. And actually, this is sort of interesting. We changed it just from 11-11 to 10-10, so a fairly minor change in payoffs, but it drastically changes the nature of the game. And now again, we get people stopping with much higher probability. So now they're playing more similar to what we might expect if they weren't confident in the other players passing. Now in this game, it actually is an equilibrium for everyone to pass, right? So if everyone passes all along, you get 10 each. That's a Nash equilibrium now. And it's a Nash equilibrium because this is the maximum top payoff you could get, so it's a best response to what the other player is doing. But it does require that you're confident that the other player will never stop at any of the nodes where they have a choice. So you can also grab the 10 early on, in some sense a safer strategy. And when we look later in the course at some refinements of Nash equilibria, then we'll actually find that certain kinds of refinements would predict that players should stop in this game, which is consistent with what we actually see in this game.